This is the beginning of chapter 8, and it's basically alternative CMOS. This section is probably quite old and possibly only of archaeological interest. And the reason for that is because vanilla-flavored CMOS tends to rule the day. And a little in-class question there is, what is vanilla-flavored CMOS? So up till now we only examined some of the basic static CMOS gates, which are most commonly used, and it's this is called for CMOS logic. But this, historically speaking, before the acceptance of CMOS in the early 1980s, which is a long time ago now, NMOS logic was a predominant MOS technology, but CMOS was preferred over NMOS primarily for power dissipation reasons. So the CMOS dissipates less power than NMOS logic. So that's sort of in quotes. As the density of IC logic increased, power dissipation became a limiting factor in IC design, and here we'll examine several alternative logic gates or logic families. And you might ask yourself why we're going to do that, and probably because, like Mark Twain said, history may not repeat itself, but it sometimes rhymes. So anyway, we're going to look at some basic static CMOS. This should be entirely review. You should know this very well. Each gate is composed of a complementary NMOS and PMOS logic network, which implements complementary functions. The PMOS section performs a pull-up function. The NMOS section performs the pull-down section. These sections implement complementary functions, and only one section will be on at a time. So if the bottom is on, the top is off, and vice versa. So the following statements generally apply to full static CMOS, and when we say static, we mean it's not dynamic. It's not charge stored on a capacitor. So the input capacitance of the static CMOS gate is relatively large compared to something like which would have been implemented in pure NMOS. Each input signal connects to both NFETs and PFETs. The PFETs are typically 2 to 3 times as large as the NFETs. That's to account for the difference in mobility. And as a consequence, the input capacitance may be in the range of 3 times that of an NMOS logic gate performing the same function. So this increased capacitance, could slightly increase gate speed. And the other thing to keep in mind is that both routing capacitance and load capacitance are important factors in determining performance. So you'd associate the capacitance of the load of being the gate of the next stage, as well as whatever it took you to route you there. CMOS uses PFETs, which are generally slower than NFETs. So the complementary PMOS and NMOS logic increases the CMOS gate area. Gate is twice as many transistors compared to NMOS, and as a consequence, each gate requires 2 N transistors, where N is the number of inputs. So in an ideal static CMOS gate, you'd have no static power dissipation. We've seen that sort of isn't the case. But the primary power dissipation would have only been during the switching. So when you're going from 1 to a 0 or 0 to a 1 on the output. The static CMOS has large symmetric noise margin, and that means it has effectively is the same as saying fully restored logic levels. The output is derived from the power rails themselves, the output values. So here's the static CMOS. This is in the need-to-know category. This is our NMOS logic block, our PMOS logic block. They're complementary to one another, and that's our 2-input NAND gate there. So that transistor level representation of the simple gates you should all know quite well. An alternative to CMOS, not a real competitive alternative, but one that you might consider as a pseudo NMOS. And the idea behind this is what an old NMOS logic used to look like, and this is a resistive pull-up here. So it's idealized, and it's called pseudo NMOS because basically you end up replacing that pull-up resistor with a P-type transistor, which is turned on, and you don't see any problem when the NMOS logic block is off. It's going to pull the output to VDD, but when one of these conducting path in the NMOS logic goes to turns this NMOS logic block on, it's basically going to be a resistive divider here, where the voltage will go low if the resistance down here is less than the resistance of that pull-up device. And this is the may not need to know category, but it's good to sort of consider some of these other structures and just be familiar with other circuit techniques. So there's disadvantages with the pseudo NMOS, and that would be power dissipation, because as we sort of saw in this situation here, when you're expressing a logic low out here, you basically have a conducting path through a resistor up here and the resistance of the NMOS devices down here, which are on. So you have to design the NMOS gates with power dissipation and noise margin trade-offs in mind. And this just goes on to discuss sort of the trade-offs between a wide PMOS transistor to implement a small resistance, but that in turn increases the static power dissipation. But if you make it not wide enough, then it's going to be slower. So that's what makes it a trade-off, and those are the kind of things you should be able to discuss, but they're sort of in the may not need to know category. There's a schematic of a 2-input NAND gate again in the pseudo NMOS, where this is a PMOS transistor which is turned on, but it's relatively resistive. So it means it's longer than a gate typically would be. The only place you may end up seeing them is if you ever look through old papers or whatever. You might see things called PLAs, programmable logic arrays, and it's likely one of the few structures where you might encounter a pseudo NMOS gate, if ever. Pseudo NMOS may be used where compatibility would be required with NMOS logic. I can't really imagine any scenario where that would be the case, but each gate only requires the N+1 transistors. And at this point in time, take a brief break.